Amir Jafari, and this is the third lecture in a series of lectures on simple harmonic oscillator. In the last two lectures, we talked about Newtonian mechanics and Lagrangian and Hamiltonian mechanics of simple harmonic oscillator. We talked about Hamiltonian, the energy of the system. We talked about the Hooke's law. We talked about damped and driven in a simple harmonic oscillator. We talked about the approximation that we call simple harmonic oscillators. It's an approximation. In reality, you're going to have some damping, some extra terms in terms of the Hooke's law. Hooke's law is the linear part of a more general, form of force. We discussed these, and this is kind of elementary. You are familiar with this from high school or your undergrad studies. And in this lecture too, we are going to talk about quantum mechanics, quantum simple harmonic oscillator, quantum mechanics of simple harmonic oscillator. In other words, we are treating simple harmonic oscillator, the same simple harmonic oscillator that we discussed before, but quantum mechanically, from the point of view of quantum mechanics. But we're going to keep the technical level simple, and any student of physics should be familiar with this, these concepts as well. But as I said before in the previous lectures, because we need these expressions, equations, concepts related to simple harmonic oscillator in other lectures, especially quantum field theory and in the future string theory, so I wanted to have some reference to these expressions, etc. So this is why we're having this elementary, series of discussions here. So let's start by looking at the Hamiltonian of simple harmonic oscillator to treat it quantum mechanically. Very briefly, I'm going to be skipping details, which presumably you are familiar with. But otherwise, you can look them up in any book, virtually any book on quantum mechanics, elementary quantum mechanics. Okay, so let's start, well, by sharing my screen, right? I almost forgot. Right, in quantum mechanics, as in Hamiltonian mechanics, you start with a Hamiltonian. You write the Hamiltonian of the system, which we did actually in the last lecture in our Hamiltonian formalism. This is the total energy of the system of this mass with some spring. We ignore or neglect the mass of this spring, and we use this idealization that the restoring force of the spring is proportional to displacement in an opposite sense, Hooke's law. And this is the Hamiltonian, the total energy for this system. P is the momentum, omega angular frequency, m the mass, x displacement from the equilibrium. This is classical Hamiltonian. This is the classical expression for the energy, total energy of the system. What we do in quantum mechanics, without going into details of quantum mechanics, which I presume you are familiar with, well, you do the first quantization. First quantization, which means that x, p, e, position, momentum, energy, angular momentum, other variables are promoted to be operators. Okay, operators, for example, the momentum is written in terms of gradient, operator h bar is the Planck's constant, I is square root of -1 complex number, and E energy is promoted to time derivative operator. And these operators are acting on what? Wave functions, for example, or states in a Hilbert space. But you can say that, well, these are acting on a wave function, wave mechanics. Let's keep things simple. Okay, so if you have a function, a wave function, which is a function of space and time, x and t, but in x representation, position representation, what you mean by this is in one dimension, for example, the gradient would be just simple derivative with respect to x. So what we mean by momentum operator is this derivative with respect to x. Okay, this is wave mechanics basically. So these are operators, but in general, they operate on vectors in a Hilbert space, states in a Hilbert space. But we are not going into such details here. These are operators now. Okay, when these are promoted to operators, the first quantization, obviously the Hamiltonian would be an operator too, because now P is an operator and X is an operator. Okay, this is the Hamiltonian. Then you say that, well, as I said before, these operators are acting on what? For example, wave function in wave mechanics. So if you say that, well, Hamiltonian acting on wave function psi, what's the result? Well, it's the energy operator acting on psi. In other words, this is p squared over 2m plus m squared x squared psi. This is IH d over dt psi. And p is given by this operator. It's defined this way. So you get this equation, this Hamiltonian basically, psi dt, right? And this is the Schrödinger's equation. Okay. Now here you have just a simple equation, and now x position operator times psi is just position of the operator times psi. So this is you should write it basically as m squared 2x squared. This is just the potential energy. And this is the Schrödinger's equation. Long story short, this is the Schrödinger's equation. So this is a differential equation. This is a partial differential equation. So you can solve it and get the energy eigenstates, energy eigenvalues, etc. But I'm not going to go into details because it's just a mathematical problem. The result is something like that. Psi xt, after solving this, would be given in terms of, with some constant, etc. It's going to be something like em omega x squared over h. So it's the potential energy basically divided by h, and then hn of m omega over h x, and it's gonna be, yeah, that's it, I guess. You can write it this way. I'm ignoring some coefficients here, some numerical factors, but this is what you get, and hn is Hermits polynomials, which are basically derivatives of the Gaussian function. So you can define them as let's define it this way. If you have a Gaussian function, exponential of minus x squared, and you're taking the derivatives, nth derivative, if you like, the result would be hnx e minus x squared, some factor of minus 1. This is the definition of Hermits polynomials. So the point is that it's easy to solve the Schrödinger's equation in this case, and this is the wave function you get. The important point, though, is that the energy eigenvalues would be given by this formula. And we talked about, h omega n plus 1 half. H bar is obviously h over 2 pi, h Planck's constant, omega is the angular frequency, which is basically k over m, square root of k over m. N is a number, a positive integer number, 0, 1, 2. I mentioned this briefly in the last lecture. So it means that in the ground state, the energy E0 is the energy of the ground state, the lowest, the minimum energy of the system is h omega over 2, but the next excited level is h omega plus the next one, you increase the energy of the simple harmonic oscillator, and you go up in this ladder for energy discretely. In classical mechanics, it is classical energy is, right? And you can show that this is, okay, the energy is conserved in this approximation, and it's a constant. Now, if you increase, if you give more energy to this simple harmonic oscillator, you basically increase, this is the amplitude. This is kx max. For a given simple harmonic oscillator with given energy, x max or amplitude is fixed, so you have a constant energy because energy is conserved, right? But if you give more energy, you excite the simple harmonic oscillator, the energy would increase continuously. So this would increase continuously. But in quantum mechanics, you see that the energy would increase discretely given by this formula. This is what you get from solving Schrödinger's equation. However, this is not what we need in our study of, for example, QFT, quantum field theory, relativistic field theory. What we need is what is called Dirac's method. And this is basically the starting point and the building block, in some sense, of quantum field theories. Okay. You say, look, the Hamiltonian operator for the simple harmonic oscillator is, again, I'm writing this repeatedly because you have to remember it. You have to know the simple harmonic oscillator upside down, the Hamiltonian, Lagrangian. For Lagrangian, this is going to be a negative sign here, but you should be familiar with all these expressions. So this is the Hamiltonian. Dirac said, look, I can simplify this Hamiltonian by defining two new operators. Remember, now you're working with operators. X, position, and P, momentum, are operators, and Hamiltonian too. So we can define two operators for simplicity, basically, this way. X plus I P over M omega, M omega 2H, X minus IPM omega. So, and well, you can write also X and P in terms of these operators. So it's easy to get them, right? You can write X, okay, it seems H to omega. I have to check that you can see all this screen I'm using here on my iPad. So you can write them this way. P, hopefully I got all these negative and positive signs correctly. Okay. So basic like change of variable type of thing. If you do this, what you get for Hamiltonian, and by the way, because X and P from quantum mechanics satisfy this commutation relation, from this easily it follows that AA dagger has operators. And by the way, I'm gonna put H bar to unity and also C. We're not going to need speed of light, but the reduced Planck's constant, H bar, can be set to unity. This is called natural units. So sometimes I do this, sometimes I don't. I said before in another series, I guess in a lecture on quantum field theory, I said that I do this for two reasons. Because I'm lazy, sometimes I forget. But sometimes I do it on purpose because you have to be familiar with all these, different forms of these expressions. It's in practice, in real calculations, in quantum field theory, in condensed matter physics, in particle physics, no one write these, constants, h bar, speed of light, c, etc., using natural units, where you put these constants unity, you set them to unity, and whenever you need them in any expression, you can recover them basically by simple dimensional analysis. Okay, so this is important that you have the commutation relation for uh, these operators, and then it's easy to see that the Hamiltonian that we had before here can be written in terms of these operators as this expression, and you can define, it's common to define a number operator, which is basically a dagger A. It's an operator too, remember. So why we are doing this? Because now Hamiltonian is an operator. When you write this eigenvalue problem for eigenvalue equation for energy for Hamiltonian, which is this, you're looking for quantum states n in Dirac's bracket notation, satisfying this equation, this energy equation. When you do this, it follows that n acting on energy eigenstate n is going to give you n as a number times n as a quantum state. So this is what n is an operator that counts the number of excitations, the energy excitation level n in your system. And also it turns out that these are easy to check, and you can find them in any textbook on quantum field theory, as I said before. You're going to get this relationship, and for A, these are really elementary to get, so I don't go into details. But the important thing here, which is going to be useful for us in other lectures in the future, is that if you look at this energy relation, from here, En is, as I said before, without proving, this is the proof, En from this Hamiltonian for energy state, eigenstate n is given by this expression, and we talked about this. So unlike the classical simple harmonic oscillator, quantum simple harmonic oscillator, when you increase energy, the energy increases discretely, not continuously. So here you see that when you apply this operator, which is called creation operator, to state n, you are jumping from energy state En to En plus 1, which is En plus h omega. So you are adding a quantum of energy equal to h omega. When you're acting this A, which is called annihilation operator, on energy eigenstate n, you are jumping from En to En minus 1. So you are going down in energy by a unit h omega, okay? Now, if you look at these expressions, these are the main results we need. You'll see that, well, what we have here, we have a simple harmonic oscillator, M, okay, and it has some energy. It is like energy, say it's on the nth excitation level, nth eigenstate of Hamiltonian. It has this energy, n plus 1. If you increase the energy of this simple harmonic oscillator a little bit, you can jump on a n plus, which is h omega n plus 1 plus 1/2, which is basically En plus h omega. If you lower the energy of the simple harmonic oscillator, as I said before, you are going to jump to En minus 1, which is h omega by this formula here, n minus 1 plus 1/2, which is basically En minus h omega. So, and if you increase energy or decrease energy by, larger amounts of energy, you are basically increasing and decreasing energy by different quanta. Okay, 1 h omega, 2 h omega, 3 h omega. So in some sense, you can say that simple harmonic oscillator, the system, has or contains n quanta of energy or n particles in it. You can imagine simple harmonic oscillator, either as a simple harmonic oscillator, which is a system with a definite energy, if it is in a definite energy eigenstate, like these formula, or equivalently, you can say that no, it's not a simple harmonic oscillator, it's a bunch of particles. Okay, so when I have energy equal to En, I have n quanta because En has nh omega plus E0. This is basically the energy of the ground state, right? So when I start from E0, basically you can say this or something like this. I have no particles around, okay, then the energy is no excitation. No excitation energy in this simple harmonic oscillator means that in some sense I have no particles around because n is 0 here. So I interpret n, this number, as number of quanta or particles in this system. Then you say that I increase energy a little bit. I go to E1, which is h omega plus. Then you say, well, I have created one particle. Okay. Then you increase energy, you go to E2. Then you say, which is 2h omega plus h omega over 2, the ground state energy. Then you say that I have two particles, so on and so forth. So simple harmonic oscillator can be thought of as consisting of n particles when it is in the nth excited level of energy. This is the basis for a starting point in some sense in quantum field theory. We can imagine putting one simple harmonic oscillator at every single point in space, okay, and every single harmonic oscillator has this energy. Where is that? This one. This is the formula. So you have En here, which is NH H omega n plus 1/2 here. Another simple harmonic oscillator a little bit further away in another point, n plus 1/2, or let's call it M, another simple harmonic oscillator, K, H omega. I'm using different NMK in order to show that these are different simple harmonic oscillators, independent simple harmonic oscillators in space. And you have infinite number of these. Then you say that, well, I need to create a new particle. In quantum field theory, we are trying to combine special relativity with quantum mechanics. And when you try to do this, you see that E equals mc squared, the equivalence of mass and energy, gives rise to a problem here because writing down differential equations like the Schrödinger's equation doesn't work there because in those equations you are basically dealing with a wave function for a fixed number of particles. But E equals mc squared means that if you have enough kinetic energy in your particles, you're dealing with, fast energy, basically particles in a relativistic system, then E equals mc squared would mean that new particles can be created all of a sudden at any point in space and time. So in order to have a formalism to treat this problem, you say that, well, I have simple harmonic oscillators everywhere in the space, and when I try to create a particle, I increase the energy at that point in space, okay, and that means that from E0 in that simple harmonic oscillator, I go to E1 by creating one particle, okay. if I spend more energy, I'm gonna create two particles. So different excitation levels of that simple harmonic oscillator at that point in space are interpreted as creating new particles. Okay, this is the basis of quantum field theory in position representation, in canonical formalism. Okay, so this is one example of why simple harmonic oscillator is very important in physics and also in condensed matter physics and string theory, etc. This is a very useful concept. I guess at this point we've covered everything, but the last word would be about the um, how we moved actually from classical physics to quantum mechanics. Here, by the way, when we treat simple harmonic oscillator quantum mechanically here, I should have added this fact that A and A dagger as quantum operators should satisfy the Heisenberg's equation of motion. Okay, uh, the same equation for a dagger, and from here you get a t, which is time dependent. I mean, the operator at time t, e minus I omega t a 0. So if you know the operator at time 0, at any later time t, you can get this operator. And also for a dagger, it would be plus I omega t a dagger 0. Okay. So now remember that we have these relations for x and t, right? And these are basically, in Heisenberg's picture, time-dependent operators. So what we have is x for the position. We write it in terms of a t a dagger. Now see that a t is a 0, e minus I omega t plus a dagger t e plus I omega t. This is what you get for the position operator, right? And then in Heisenberg's picture, and for the momentum as well. So this is the starting point to write down a free field, or any field actually, at a given time in quantum field theory in terms of creation and annihilation operators. And if you look at the classical solution, we got something like this, a constant EI. So this is quantum mechanics, this is Newton, or classical mechanics. We got a solution like this. Here, A and A star are just numbers, probably complex numbers. So you're going to get the real part of this, but this is not important. You can, in general, the solution of the equation of motion for simple harmonic oscillator can be written in this way. You see that from moving from classical, in moving from classical mechanics to quantum mechanics, what you do basically is to make these coefficients operators. And this is related to first quantization because you're making x an operator, right? And also other quantities like momentum and energy. These similarities and expressions are very useful when we treat quantum fields. So this is the reason that I wanted to say a couple of words here. I guess that's it. And in the future, probably we'll add another lecture to these to cover some other concepts related to simple harmonic oscillator, for example, about path integrals. But for now, I guess you're good, and this can act as a reference for our lectures in quantum field theory and string theory.